And I'm old. Okay, I can live with that. There's pizza up front. Help yourself. There's pizza in Matt's lap. Help yourself.
See, I'm helping people out. It's close over here.
He needs the exercise, or at least I do.
Okay.
Jeez, there we go.
Huh? Jesus, I know. Dude, I'm getting extra credit for being there yesterday.
You're getting extra credit for being in class? Did you say you're getting extra credit for coming to class?
Well, no, actually, I ran into my Dr. Butler.
Yeah?
Chris came over and we had pizza.
His wife's there with the kid. It's Friday. We bring pizza on Fridays. All the visitors, this is a normal Friday occurrence. Thank you, sir.
Kenney, did you post the list of the bonus
The list of?
opportunity thing?
Not yet. I forgot to do it. Mm-hmm. I'm sorry? Sausage pizza down here, those who wanted some meat. Jess, any announcements today? The easiest targets, yes.
Hi guys, there's an SI session on Sunday in the way tutoring room like usual. It'll be Strav. Keep in mind next week's an exam week, so you have to take a test soon. So you might want to learn how to do the chemistry before you take the test. Also, if you lost a video, it's up here, and I'm still selling an iPod for $60. So
What
let me know
kind
if
of
you want
iPod
it.
is it?
The one I found.
You know, show it to me. I might want it. All right. I'm already buying a refrigerator from one student. Israel and Palestine. Well, you know what? I'll take the iPod and I'll go buy $200 headphones. Oh, well, you can go to Target for those. How much?
I found a set on Amazon exactly the same for 50.
eBay, okay. I'll look for it. Amazon? It's all right. All right, folks. It's obviously Friday because we have pizza. There is still pizza here. Thank you to Juniper Residential College for contributing the pizza that was left over from the wall. Those who participated in the wall activity, thank you. I have been receiving some of your reflections. I'll keep collecting those from you. If you were there to help pull the wall down, you found out that it wasn't quite as trivial to pull down as we might have thought. There's a piece of it up in my office, though, so again, thanks for those who participated. I will find time somewhere to post for you the bonus opportunities. I thought of another one after I left yesterday. Next Thursday, is the research showcase. Is it Thursday or Friday? Friday. Is the 16th, so it's Thursday and, no, it's Wednesday and Thursday? Wednesday and Thursday? Yeah, I think it's Thursday and Friday, though. Okay, it is Wednesday, Thursday. Thank you. If you attend the research showcase, and I strongly encourage you to do so, and then write a reflection on it, that's outside of a seminar, so that's an additional one beyond those. Sheila Pedigo, who runs the source program here at CASE, is always looking to find a way to introduce the SOURCE program to more people. If you don't know about SOURCE, I strongly encourage you to look into it too. SOURCE is going to provide funding for undergraduate students for research and creative endeavors, the RCE part of SOURCE. So it's a place where you can get funding for projects. And when is it? It's next week. And it's over in Veal. So.
Last night tonight they're doing the tryouts for Hudson Relays. Is that still bonus?
Yes, tryouts for the Hudson Relays is still bonus. They'll send me a list of all the people who tried out. And remember, all you got to do is show up. Those of you who are second-year students, you have to show up for your tryouts, and then you have to let me know that you were there, because the first-year students, who the bulk of you are, they'll send me the list. So I will also post this weekend recommended problems from the chapters for you to do, so that you have some things to work on.
Are you planning coaching as well?
I am, thank you. The other is, last fall, one of the things I said was athletic events and or cultural entertainment type events. It's not that I don't like baseball and softball and all those other things, folks, but if you attend one of the plays, the musical performances, Tartuffe in particular, that is worth a bonus. Does Chicago count? No, it's from today on. Sorry, Chicago was worth going to. Not that Tartuffe's not.
So you can only do that once then?
Only once. Only one of those. And I'd rather not have you all skipping school Tuesday to go to, what is it called, Progressive Field now, to watch the baseball game. Although, if you do decide to go to Progressive Field, make sure you get your free ticket off of the web.
There's a wind ensemble concert this Sunday at Hartnett at 2:30.
Wind Ensemble at Harkness, definitely worth going to. There's another free concert.
And in Severance the Sunday afterwards,
That-
which is the gala, which has
Everybody.
wind ensemble, vacation, funny, and symphony orchestra.
There, as soon as we're done here, I have to go. I don't have to. I am part of the first-year cohort, so I'm going to a meeting of that. And they're actually asking faculty around campus to share with students. If you could share one thing with students, what would it be? And so I get to decide what to share with students. So, take Chem 105 and 6, right? 105. Forget 106. All right. Your test next week will be over chapters 18 and 19. Okay? What says what? Through 20.4 on the syllabus? What's chapter 20? Well, Tanya says, yeah, we want to go through chapter 20. There, everybody, this is Tanya, by the way. No, it will be through chapters 18 and 19. I'm sure that I can do enough with thermodynamics and electrochemistry to cause you enough pain and anxiety. So, did I say it was going to be no, I didn't say an easy test. I said easier. There's a difference between easy and easier. I did not say it was going to be a gift. That's good, Mary. That's a good try. But I did not say it was going to be a gift.
Remember that we have everything that you ever said.
I know it. It's all on videotape. Which reminds me, I'm going to throw out a suggestion I'd like you to think about. I'd welcome feedback. This is the first year that I've been at Case that I've actually been able to say, okay, next year, and so I want you to look out for next year's students for a second. Matt?
If we suffer this.
Well, they'll suffer enough. They have to take my class. I'm sorry? I know, there's some visitors here. That's right, there's some visitors here today. This is the first time in a long time that I've been able to, it's the first time that I've ever had the entire semester, or the entire year videotaped. So all of these lectures are now on videotape. And I'm using the same book next year. So one of the things that I'm contemplating doing next year is saying, you know what, if you want to see a lecture about this material, it's online. Instead, I just want to answer questions every single day. I don't ever want to come in and do what I'm going to do today, next year. So I don't want feedback today. I want you to think about it. But Wait, let me finish. I know, it's benefit for them. They don't have to listen to me, right? We are going through and looking at all the videos and saying, here's a keyword search for the video. This is what you'll find on this video. It's on these sections of this chapter. So if a student says, okay, I want to find about chapter 3, sections 1 through 4, I watch this video. And so they'll be able to get all that stuff. But then we can come in and we can talk about fun stuff. We can answer problem questions. And so we eliminate you sitting out there, and instead I get you doing the work. Actually, not you guys, them doing the work, so that I can be lazy. You don't have to watch the video because not every single one of you learns through lecture. Because if you did, attendance today would be about twice what it is. There's also statistics that will be coming out shortly that shows your grade is directly correlated to the number of hours you watch Media Vision, which leads me to say, well, if that's the point, let's just watch Media Vision. There was a class that was taught at Michigan State University where the professor sat in the front row and watched himself with all of his students on the video. Now, I would never, well, maybe, no, I won't do that. But can you believe it? He just sat here with everybody else and watched himself. And then he'd get up for the last 10 minutes and lend clarity to some of the stuff that didn't make sense. In other words, he should have had half an hour for the half-an-hour presentation. That's craziness, but there was one person who did that.
What about those of us who never watch Media Vision?
What about those who never watch Media Vision and still do well on the tests?
Like we just come to class and read the book and don't ever watch Media Vision.
The other thing I'll tell you that I'm doing next fall that I did not do this year, but I will find a way to do next year, is there will be a test on the first day. Actually, there may be two. One of them will be a test to show me where everybody's at to start, but then the other one will be, what is your learning style? I'm a strong believer in a learning style inventory, and I know what my learning style is, and I know my preferred method. So one of the things I was going to do today is actually pull up a website that has all this information on it, but it allows me to jump from here to there to there, to go whichever way I want. To me, that makes sense. To many of you, you would say, don't do that. You want it linear. You want it one thing after another. I'm not that way. I prefer things all over the board. And so we're going to try a combination of the two today. So think about that. I'd welcome feedback on that. Those three of you who are in here who are SIs next year, especially from you guys, what you think of that. So, I'm sorry? Actually, there's 4 of you in here who are SIs for next year. 3 new ones and a returning SI. Now there are 6 SIs between my 2 classes. I have 3 in each class.
So there's 2 in here?
There are Jessica, you, and Lindsay are 105, 106 next year, and Michelle is doing 111 in the fall. Michelle suffered through 111 last fall, not 105, and then came to 106. Somehow she decided engineering wasn't for her. So, all right, let's talk about electrochemistry and get some specifics taken care of. Please have more pizza before we leave.
Oh my God.
Matt, how much have you eaten? That tray was full when you started, Matt. There's 2 pieces left on it. All right. We've talked about some of the fun things. Let's get rid of some of the specifics now. There is a very simple equation in your book that talks about how to calculate the amount of potential energy, or the cell potential, for any electrochemical cell. It's also on your equation sheet, and I want you to forget it. Very well done, Matt. Thank you. I'm not, no. And part of the reason I want you to, I'll write, can I even remember what it is? I mean, it's such a simple equation, you don't even have to work to remember it. E cell equals E cathode minus E anode. However, it's kind of like the Henderson-Hasselbalch equation. It's a very simple equation that is very easy to use wrong. And the reason why it's easy to use wrong is that minus sign. So the first electrochemical cell that we talked about on that first day was this one. It's the Daniell cell. It's copper ions reacting with zinc to form copper and zinc ions, not solid. And if I want to figure out what is the cell potential of that electrochemical cell, what I've got to do is get a table of electrochemical cell potentials. These are always written as gain of electrons. Gain of electrons is they're always reductions, and they're done that way simply because it's easier to just list all reductions instead of both. If you look at old enough books, you'll find oxidation reactions, but most of them are written as reductions. But if I take this reaction then and I say, okay, what are the reductions? The standard half cell potential for that is 0.34 volts. This half cell potential is negative 0.76 volts. And when I combine the two of them, they're both written as reductions. I need one to be an oxidation and one to be a reduction. I could reverse either one of these reactions and then combine the two and write a reaction that would indeed allow me to calculate a cell potential. All I have to do is once I've reversed one, I change the sign on it, and then when I add the reactions together, I just add the cell potentials. Okay? So I'm going to reverse the second one. Since I already know that's what's going to happen. And all I have to do is change the sign on it. Now if I combine this first reaction with this second reaction, I will get what I'm interested in. And so the cell potential, how much voltage is there in that reaction, is just this number plus this number. Remember the equation over there said minus? I took care of the minus when I reversed it. So don't worry about the minus. Just make sure you have one reaction that's a reduction, one that's an oxidation, and if you've done that, just add the cell potentials. Well, a typical question would be something like this. So I've got iron and magnesium. Calculate the spontaneous cell potential for the reaction of iron and magnesium. Okay? Spontaneous being the key word. This is a reaction that has a delta G less than 0. There's a very nice simple relationship, which is an equation you should know. That says that the free energy change of any reaction is the number of electrons being transferred times the Faraday constant, 96,500, or 96,485, times the cell potential. Okay? So if E is positive, delta G will be negative. And so that's what we want. We want a spontaneous reaction, so we want a positive E so that we get a negative delta G. Well, the way I'm going to do this is I'm going to take my cell potential table, and I'm going to look on here for magnesium and iron. Here's one, magnesium. E0 is negative 2.38 volts. Iron. There's iron 3. There's iron 3. Looks like that's my choice. Oh, there's iron 2. How do I know which one to pick? I don't. I'm just going to pick one. I wasn't that specific. They're both negative this time. I have to reverse one of them, and I'm going to pick the one that when I reverse it and I add the two reactions together, I get a positive number. So I'm going to reverse the magnesium reaction. Is that right? Yeah. So if I reverse the top reaction, add it to the second reaction, that's what I get. Why does it matter which way you write the reaction? Okay, let's see. Let's look at this one. Let's go to an extreme. Lithium. Atomic number 3, upper left of the periodic table, 1 valence electron, very low electronegativity. What do you know about lithium in terms of its ability to lose electrons? It's really easy. It really wants to lose electrons. It will give up its electrons to become just like helium. So if I take that, and I remember delta G being less than 0 is spontaneous, is this a spontaneous reaction? No, lithium ions won't pick up electrons. They like being lithium ions. They try to lose electrons. Lithium would rather lose its electrons. So if I wrote this the other way, I would predict that this one has delta G less than 0. This one up here has delta G greater than 0. You have to work to get a lithium ion to pick up an electron. Its electron affinity is extremely low, but its ionization energy is also very low. It gives up electrons very easily. Okay? Well, if delta G is less than 0 for the second one, looking at this equation, N always has to be positive, F is always positive, so that means E has to be negative. And in fact, now it's 3.08. Okay? So the sign on it gives you a sense of how easily does it lose electrons. Take the other extreme. Fluorine gas plus 2 electrons to make 2 fluoride ions. Fluorine's in the upper right of the periodic table. It's got a very high electron affinity. It wants electrons. It's small, so it grabs them easily. Would you expect this to be a positive or negative delta G? Why negative, Shar? This one's going to happen. It wants to pick up electrons. So if it's got a negative delta G, it has to have a positive E0. And if I go to my table, it's the last entry in here, and it's 2.87 volts. These are the two extremes, by the way. This is the most negative reduction potential. This is the most positive reduction potential. That's the entire limit on the whole periodic table. Nothing has a more negative value. Nothing has a more positive value. So the most potential you can get, the highest voltage you could get out of any sets of half reactions is 5.95 volts. It would be those two reactions coupled together. So when you talk about a 12-volt car battery, it would have to require at least 2 electrochemical cells, at minimum. There's no way to get 12 volts from one reaction. Most reactions are somewhere between 0 and 5, and most of them are around 1.5 to 2. And so that's why car batteries are 6 electrochemical cells. What happens if I do this? since fluorine is such a stable diatomic element, why would it want to pick up a couple of electrons? If there's electrons around, fluorine will pick them up because it would rather be a monatomic ion than to be a diatomic molecule. That's why. Chlorine also will become ionic. Chlorine, again, because of its high electronegativity. As you go down the periodic table, that's not as true for bromine or iodine. And so on the cell potential table, they'll have lower values, absolute values. Okay? Do the same problem, but now do it for aluminum and magnesium. Well, we can take that same cell potential we had for magnesium over there, magnesium and 2 electrons, that's negative 2.38 volts. Aluminum plus 3 electrons. I have to pull out this data table. You will be getting a data table like this on the exam. Let's see. There it is. Negative 1.66 volts. So when I combine these two, I'm going to have to multiply one reaction by 3 and the other by 2. I have to reverse one. So let's see, I'm going to reverse the top one. And I'm going to multiply this one by 2. And when I add the 2 reactions together, the electrons will cancel out. What do you think? Why not? You just think it's a good idea not to? I did tell you not to. Do you remember why you don't multiply the potential? The cell potential here is plus 2.38 volts. The cell potential here is negative 1.66 volts. Add them together, we get 7.72 volts. Why don't you multiply by 2? They are intensive. Very good. Claire got that? They're intensive variables. They're independent of the amount you've got. But it's also because of this. If you remember they're intensive, great. But because delta G already takes into account the number of moles of electrons through this N, I'm not going to multiply this by 2 as well. I'd end up doubling the effect. And so everything goes back to delta G. Yes, you double delta G if you double the reaction, but it's because there's twice as many moles of electrons being moved when you double the reaction. You don't have to change the cell potential. So that cell potential is 0.72 volts. About the only thing we haven't done is we haven't shown you how to sketch these and draw the shorthand. So I want to do that. For copper and zinc, the way that I would do this in the lab is I'd set up 2 half cells. Just like the chemical reactions are going to have 2 half reactions, I'm going to set up 2 half cells to this electrochemical cell. And the reason I do that is because I want to make sure that I isolate things so I don't set up any short circuits. Short circuit just being electrons will always follow the path of least resistance. And so if I have a short circuit, they're going to follow that path as opposed to the one that I want them to do. What I want the electrons to do is I want them to go through this device, whatever it is. If it's a meter, if it's a light bulb, if it's a motor, it's something. I want to make sure the electrons go through there. And the current, which is the flow of electrons, will determine whether or not the size of the current will be determined by how big a load is that device. If it's a motor, you need a higher current. If it's an LED light, you don't need a very high current. There's an article in, where did I read it? Newsweek this week that talks about how many of us are switching over to CFLs, compact fluorescent light bulbs. They're great. They use about 30% of the energy of a regular tungsten light bulb, but they have a problem. Mercury. They have mercury in them. So all of us who've gone out and bought CFLs, and yes, I have them in my house, have now got mercury that we're going to have to dispose of someday. Well, there's a new technology that'll be out hopefully this fall that uses LEDs. And they use about 1/10 as much energy as a tungsten light bulb. But they're having trouble getting LEDs that give you a nice bright white light. So that's what they're working on. My daughter just came home with a book light that's an LED that's very bright, intense white light. But you know what it's got in it? I've opened it up to check it out. It's got two 1-inch in diameter NiCad batteries in it. So this little book light has two huge batteries that don't have a whole lot of current flowing through them, but a lot of voltage. So these bulbs are going to require a lot of energy, a lot of voltage in them. And I don't know that they're going to work as well in a house. Anyway, back to this thing. Here's where I put my zinc electrode. Here's my copper ions. Based on my reaction that I have, that's all I have to have in order for this reaction to occur. Right? I just need a source of zinc and I need a source of copper ions. I have to complete the circuit. So I put a connector in between them. That connector is the salt bridge. We talked a little bit about this. The salt bridge allows ions to transfer back and forth. Because what's happening? As the zinc electrode starts to dissolve, we'll get zinc ions building up in that solution. Electrons will start here and flow over to here. As that electrode starts to become more charged, more negative, the copper ions will start to come out of solution and coat the outside of that electrode. Okay? That's the chemistry that's going on. Now, if you think about what's happening, we're increasing the positive charge in this solution. This solution, the copper ions are coating the outside of this electrode, so we're decreasing the positive charge here. We're increasing the negative charge. So let's say there's nitrate ions in here. Now there's going to be too many nitrate ions. Over here there's excess positive charge. So what happens is anions will flow through the salt bridge from the right cell to the left cell, and at the same time cations will flow through the salt bridge from the left cell to the right cell. That salt bridge is a great big resistor. If you think about it, in order for those ions to move through there, they have to avoid colliding with each other, because if they collide with each other, if they, heaven forbid, precipitate, then you really have a problem. But if they don't, which is why you use nitrate a lot of times, or sodium ions, but if they collide with each other, they're going to slow each other down. If they slow each other down, the circuit gets slowed down. It's kind of like the beltway. Those of you who are familiar with the DC beltway, about 10 years ago, there was an individual who decided that he'd had enough of life, and so he stood on the Teddy Roosevelt Bridge to jump. And the highway patrol said, "We can't let this happen. We're going to stop traffic on the beltway." Okay, the Washington, D.C. beltway just goes all around D.C. And all of a sudden they stopped traffic on one end of this thing. It's literally a big circle. Guess what? It then backed up traffic on the entire beltway, all the way around 11 miles. Nothing moved. It took me 4 hours to get home instead of the 30 minutes it should have. And I didn't even get on the beltway. But this is the same kind of thing. If you stop it for some reason, the current doesn't flow anymore, your battery's dead, you no longer can use it. We want that thing. So if you design a salt bridge, you have to think about how do you get things to flow through it. Yes, he did not jump. As a matter of fact, actually 2 years later, after he had gotten his life in order and he was feeling much better about himself, he went back to the bridge. Yes, traffic backed up yet again. However, this time, it was because of all the news reporters there congratulating him for getting his life back in order. So, now, that happened 3 months before the truck carrying black powder tipped over as it was going around a curve. So there's black powder all over the Capitol Beltway, and that shut down the entire Beltway too. But that happened at 6 o'clock in the morning, and so they closed school, my wife's school, said that because that was the evacuation center in case there was an explosion. There wasn't. DC's a fun place. Anyway, as this thing flows current this way, if you've got lots of electrons flowing, it's like a car battery. Remember, a car battery is designed so that you get lots of current in a short burst. Think about how that car battery was built. You've got pieces of lead and lead oxide interspersed together, and surrounding the whole thing is sulfuric acid. There is no salt bridge in a car battery. The reason why there doesn't need to be is because the two electrodes don't interact closely enough with each other. And so you get this huge burst of current, electrons flowing through it. But in a 9-volt battery, there we go, there is salt bridges in here, because if there weren't, this thing would be continually losing energy, and it is anyway. Anytime it's sitting on the shelf, it's losing energy. The chemical reaction is happening. But we want that current to be controlled to some extent. And so what's inside of these in a AA and a AAA battery is just saturated notebook cardboard, actually. If you take the backing on a notebook, that's what is inside of here that's got the electrolyte in it, the ions. The difference between the AA and the AAA battery is how much chemical is in it. If you put more chemical in it, you get more current. And so the bigger battery can give you more current. A smaller battery doesn't. Anybody got their calculator handy? We haven't done any calculations, but that's okay. James is right here. You open up your calculator, and you've got 4 AAA batteries in here. Okay? And that's a nice solar calculator. I like that one. There's also a little screw in here, and underneath it, there's a NiCad. There's a nickel-cadmium battery. Why do you need both? These 4 batteries, which are bigger, are more current. They power the display. The display is a huge current draw. The NiCad underneath powers the electronics that tells it, when you push this button, do this. You don't need a lot of current for that. But what you do need is a significant amount of voltage. And so the NiCad, I can't even read this, my eyes are too bad. The NiCad that's in here is about 2.2 volts, if I remember right. These are providing not a lot of voltage, but enough current to be able to show the display. How do you know when to replace them? When you can't see your display anymore. You need to put new batteries in there. I think we talked about the fact that they started freshness dating them. Well, freshness dating was just something that allowed them to sell more batteries. You pick it off the shelf and you say, oh, look, it's still good, because it's not past its freshness date. If you believe those dates, I've got some very cold pizza up here that you might like.
What are batteries? You said that when they're sitting on the shelf, the reaction is happening.
Excellent question. The battery is continually losing energy even when it's not connected to something. When you connect it to something, you close the circuit. And they do a very good job of isolating it as much as they can, but they can't isolate it completely. So it's continually using up chemicals. And as soon as the chemicals get used up, the battery is no good. Somebody asked about the rechargeable. I think we talked about it. When you recharge a AAA or a AA battery, if you plug it into the wall on those little rechargers, the reason why you shouldn't do that is because you're also heating up the battery. What's inside the battery? Water. When you heat up the water, what happens? It vaporizes. When it vaporizes, what happens? The pressure increases and the battery bursts. So you can indeed recharge those batteries, but you're taking a risk when you do it. Laptop batteries, what was the problem with the laptop batteries that recently got recalled? They were catching on fire. Why were they catching on fire? Because the resistance was too high, they were heating up. And they were actually catching on fire, the case was catching on fire. Mary? Yes. How does the battery determine it? No, I won't. Okay. The chemicals that you put into the battery determine what the voltage is. So if I want the highest voltage possible, I'm going to take my data table and I'm going to take the two extremes, the highest reduction potential and the lowest reduction potential. And that's the most voltage I could get. That's where to go, lithium and fluorine. Over there, thank you. I knew it was here somewhere. That would be the maximum. Lithium-ion batteries were very much sought after because they're light, they generate as much voltage as you can possibly get. But voltage usually doesn't matter, it's current that matters. And so the current is the number of moles of electrons that flow through that circuit. And so you want to design a battery that gets a lot of current. There's a huge current draw on a lot of things. And so that's how you determine which battery you're going to use. If you need a lot of current, you need to have something that the electrons flow easily. If you need a lot of voltage, the amount of electrons that are flowing don't matter. And it depends on the device. You can't get voltage without current. You have to have current, but it's how big is the pipe, okay? If you took physics and you talked about resistors and electrical circuits, you probably used a water analogy that said if you've got water going through a pipe, if you make the pipe smaller, the water flows slower. If I take 3 pipes and connect them together, the speed with which the water goes through it will be determined by the smallest pipe. So if I take a big pipe, a small pipe, and a big pipe, the small pipe will determine the flow. No matter how much I push on the big pipe, the small pipe will determine the flow. The pressure will be very high on the other side, so you can increase the pressure. The same thing happens in there. I can get a lot of electrons going through that circuit, a high current, but the potential energy difference is the same. The voltage is still going to be the same. Some batteries have much larger internal resistances. That's a big difference in terms of current, yes. That's the main one that we have to worry about. Temperature, though, it will determine some of the resistance. There's another thing, though, that's very obvious that will determine how much current you get. Go back to the copper and zinc battery. If I want to have a battery made out of copper and zinc, I already told you this very quickly, what do you have to have? Copper, ions, and zinc metal. Do I have to have any copper metal for it to happen? No, I don't. I'm going to make copper metal. Do I have to have any zinc ions for that battery to work? No. I'm going to make zinc ions. As I make copper and zinc ions, what happens to that reaction? I'm sorry? It goes to equilibrium. So I start with a lot of reactants and I make products. What's the value of Q when I first start? Q is equal to the concentration of the products raised their stoichiometric coefficients divided by the concentration of reactants raised their So Q is equal to 0 when I first start if I don't have any products, right? Q has to be less than K then, right? If Q is less than K, the reaction goes from left to right. Guess what? You get the highest current density when the battery is brand new. Surprise, surprise. As soon as you make some product, guess what? The current flow goes down because now equilibrium's fighting against you. What do you think happens to the cell potential as you let the battery get older? As you make product, what happens to the cell potential? It goes down. It's at its maximum when you first start, and then the cell potential declines as you use it. Well, we all know that. We watch the display on our calculators get dimmer and dimmer and dimmer. And yes, you can go and you put new batteries in, and all of a sudden it's nice and bright again. When do we know what that cell potential is? We only know it under standard conditions. What are standard condition? 1 molar concentration, 1 atmosphere of pressure, 25 degrees C. So guess what? We're going to have to come up with some equation that's going to allow us to calculate what is the cell potential at different concentrations. It's possible to make a battery work because you've got a high concentration of reactants and a low concentration of products. They're called, surprise, surprise, concentration cells. The higher the concentration, the greater the cell potential. You've all used one more than likely. It's called a pH electrode. How does a pH electrode work? That reaction, or that equation. What it does is it says, okay, if I know what the chemical reaction, and it really doesn't matter what the chemical reaction is, it's actually this one. I can write a value or an equation for Q. It's the same Q as before. R, 8.314 joules per mole K, the temperature you do it at, the number of moles of electrons that can transfer, the Faraday constant. This is the standard cell potential. Well, what does this say? It says if Q, if you've got lots of reactants and not very many products, Q is less than 1, the natural log of a number less than 1 is negative, negative of a negative is positive, and so the cell potential will be greater than E standard. If you get too many reactants, it's going to be the exact opposite. N for that one? What do you think? How many moles of electrons? 2, so it would be 2. Anybody know the cell potential of that reaction? 0. This is the reference. Everything is reference. It's impossible to have an oxidation without a reduction. They have to be done together. Well, if that's the case, there's absolutely no way you could ever figure out what cell potentials were unless you said, we're going to arbitrarily pick one to be 0. The arbitrary one we pick is what we've always picked on. Hydrogen is the atom left out. We don't care about hydrogen. We're going to say that the cell potential for that reaction, whether it's forward or reverse, right, is going to be 0 volts. And as soon as you set up a reaction with that electrode, then whatever you measure is the cell potential of the other thing. Here's your challenge to think about over the weekend. How am I going to plug an alligator clip, clamp it onto the hydrogen gas? If that's my electrode, up there I could easily see putting an alligator clip on a piece of copper or zinc or copper. How am I going to get an alligator clip to clamp onto some hydrogen gas? Huh? Help yourself to some pizza if you want some on the way out. Come on, Matt, take a few more.